In the previous video, we talked about the probability of two events happening one after the other, and that looked something like this. The probability of event A happening in the first experiment and then the event B happening in the second experiment turns out to be just the probability of event A happening in the first experiment multiplied by the probability that event B happens in the second experiment. But as it turned out, this second probability, the probability of event B happening, was often affected or changed by event A happening in the first place. In other words, this probability can change if the events A and B are dependent on each other. So technically, this probability here should really be read as the probability that event B happens given that event A already happened. And this type of probability that depends on some other event happening has a name. It's called a conditional probability. And we actually have a slightly new notation for it. We might more correctly call this second probability the probability of B happening given that A happens. And that's what this notation means right here. Let's generalize a little bit. The probability that some event E2 occurs, given that event E1 has already happened, is written like this right here. Probability of E2 given E1. Let's take a look at an example. So we're given these 6 circles. Each number is either colored black or red. Each circle is either colored green, orange, or yellow. And we want to find the probability that the number is black given that the circle is green. Well, first let's write the notation. We want to find the probability that the number is black given that the circle is green. There are going to be a lot of ways to do this, but one way to do it is to start by assuming that the circle is green. So we can go up here to our sample and look at all of the elements that have a green circle. Then we can just focus in on those 3 green circles and ignore everything else. And then ask the question, what is the probability that our number is black? Well, we have 3 green circles total, and of those 3 green circles, there are 2 that have black numbers. So our probability is going to be 2/3. So if we're already given that our circle is green, the probability that our number is black is 2/3. Let's take a look at the next one. We want the probability that the number is even given that the number is red. The notation is, we want the probability that the number is even given that our number is red. And what we can do is start with the assumption that our number is going to be red. So we can look up here at our set and find the elements that have red numbers. It looks like we just have 2 of those. Now we can ignore everything else and ask the question, what is the probability that our number is even? So we're given 2 possibilities total, and one of those 2 numbers is even. 6 is an even number and 5 is an odd number. So if we start with the assumption that our number is red, we have a 1 in 2 probability that our number will then be even. Well, there's actually a formula that we can use to find these probabilities. So there it is right there, and it looks a little bit complicated at first. This formula says that the probability that event 2 happens, given that event 1 happens, equals the number of times that event 1 and event 2 happen at the same time, divided by the number of times event 1 happens. Let's take a look at these 2 examples to investigate this formula. For our first example, you can see that event 1 is our circle being green. Event 2 is then our number being black. That means that using this formula, our numerator should be the number of times that these 2 events happen at the same time. The number of times our number is black and our circle is green. And based on our formula, our denominator should be the number of times event 1 happens. Well, what is event 1 again? It's the circle being green. So our denominator should be the number of times that our circle is green. Well, if we look back at our sample, that's actually exactly what we did. We first found the number of times our circle was green, and we looked up here and we decided that number was 1, 2, 3. That number went in our denominator, and then in our numerator went the number of times that our number was black and our circle was green. It looks like from our sample that happens 2 times, so that's why we had a 2 up here in our numerator. Taking a look at our second example, event 2 is our number being even, and event 1 is our number being red. In our denominator, we should have the number of times that event 1 happens. That should be the number of times that we have red numbers. Looking up at our sample, it looks like that happens twice. That's why we have a 2 in our denominator. Our numerator should then be the number of times in our sample we have both a red number and an even number. Looking up at our sample, it looks like we have a red and an even number just once, just this 6 here. So that's why we have just a 1 in this numerator. Okay, so as it turns out, that formula works pretty much the exact same way we were looking at the problem in the first place. Let's do one more example. Let's find the probability that the number will be red given that the circle is orange. The notation for that would be probability that our number is red, given that our circle is orange. So if we're given that our circle is orange, we have to start by looking up at our set and finding all of the circles that are orange. And it looks like we just have this 1 right here. That means that our denominator is just going to be a 1. Then focusing in on just that one element, we need to ask the question, what is the probability that our number is going to be red? Well, we only have this one element to look at, and that number is black. It's not red at all. So we have no times when our circle is both orange and our number is red. So we get a 0 in the numerator. Our probability is 0 over 1. 0 divided by some number is just 0, and that's going to be our final answer there. Let's move on and look at another one. Here is our spinner, and we spin this thing and it randomly lands on a number. We want to find the probability that the spinner lands on blue, given that the number is even. The notation that we use for that is the probability that we land on blue, given that our number is even. So we have to start by assuming our number is even. How many options do we have up here that have even numbers? Well, I see 2 and 4 and 6 and 8 and 10 and 12. Those are all even numbers. That is a total of 6 elements up there that have even numbers. Now, out of those, how many of those spaces are blue? Well, I only see this one right here. So only one of those 6 even numbers is a blue space. So our probability is going to be 1/6. Again, if we wanted to think of this using the formula, this numerator is going to be the number of elements that both have an even number and are blue, and I think that is confirmed right here with this 1. And this denominator is the number of elements that are even. I think that checks out. The next problem asks us to find the probability that the pointer lands on a number greater than 8, given that it lands on blue or purple. So that notation is going to be the probability that our spinner lands on a number greater than 8, given that our spinner lands on blue or purple. Okay, I'm going to erase these circles up here so it doesn't get too messy. We first want to assume that our spinner lands on either blue or purple. Let's circle all of the numbers up here that have either a blue or a purple space. All right, those are all of our blues and our purples. That is a total of 7 numbers that are either blue or purple. Now, focusing just on those numbers, how many of those are greater than 8? Greater than 8 does not mean equal to 8. It means greater than. So 9, 11, and 12 are all greater than 8. That was 3 total numbers that were greater than 8 out of the 7 that were either blue or purple. So our probability is 3/7. Let's look at one last example. For this example, we're going to be using one of these tables. Sometimes these are called two-way tables or contingency tables. And this table has some data in it. Some people were given a survey at lunch and at dinner, and they were asked if they got good service or poor service. You'll notice in this column right here, we have all of the people that said that they got good service, and that number totaled to 1,452. Of those 452 people, 508 of them were eating at lunch, and 944 were eating at dinner. You can see along the bottom of this table, we have all of our totals, and the same is true on the right side of the table. And just to make sure that we're clear here, as an example, of all 2,401 people that were surveyed, 329 of them said that they received poor service at lunch. All right, now let's see if we can answer some questions. Let's find the probability that poor service was provided given that the meal was at lunch. So, the notation for this is the probability that we're given poor service given that the meal was lunch. So we can assume that we're only talking about lunch, and the total number of people surveyed that were there for lunch was 837. Now, if we just focus in on those numbers, how many of those people said that they got poor service? Well, it looks to me like it was 329. So our probability is going to be 329 over 837. If we want to look at these two numbers using the formula, we can recall that this is the formula right here that we're talking about, and this denominator would represent the number of people who were just there for lunch. This numerator would represent the number of people who were there for lunch and received poor service. We divide those two numbers, and that gives us the probability that someone received poor service given that they were there for lunch. Let's do one more probability problem that's going to be a throwback to a previous video. We want to find the probability that the meal had good service or was dinner. This is now an OR problem. So if we can recall our previous formula for OR problems, there it is. That came from the and or video that we just watched previously. And if we use this formula, make a little bit of room here, that's going to look like this. The probability that we got good service plus the probability that we were there for dinner minus the probability that we got good service and we were there for dinner. Okay, let's look back at these numbers and first find the probability that we got good service. Well, the total number of people that got good service was 1,452. That was out of 2,401 total people surveyed. The probability that an individual was there for dinner can be read off of this row right here, where we can see that 1,564 people were there for dinner. Again, that is out of a total of 2,401 people surveyed. What you'll notice is that we have this familiar overlap that we saw in the previous video. By totaling the 452 people and the 1,564 people, we actually counted these 944 people twice. We do not want to do that. We don't want to count those 944 people twice. So what we do is we subtract those off. We're subtracting off the probability that someone came for dinner and got good service. That is 944 over, again, a total of 2,401 surveyed. Since all of our denominators are the same, I'm just going to add and subtract the numerators. That gives us a numerator of 2,072, and then I'm just going to divide that result by 2,401. That gives us a probability of 0.863 if we round to 3 decimal places. That's the same as rounding to the nearest thousandth.